My name is Natasha Kirkham. I'm the current president-elect for ICUS, which is the International Congress of Infant Studies. And it is my great pleasure to be able to welcome you to this webinar on infant pupillometry. As you all know, because you're here, pupillometry measures the variation of the pupil diameter and the pupillary light reflex. And this measure has been used in many different fields, clinical and research, from back in the day when doctors used to use candlelight to check pupil reactivity to light. And in our field, we've used it for a variety of different investigations, looking at things like cognitive load, predictive processes, increased attention, et cetera. Today, we are really lucky to have an incredible team from the University of Copenhagen in Denmark with us today to talk about how to navigate the full pipeline from experiment design to data analysis. I'm going to introduce very briefly each speaker, but they'll obviously tell you about themselves and their work when they come up to give the talk. We have Emanuela Jung, who is an assistant professor in developmental psychology at Copenhagen. Her research interests have centered on using pupil size as an index of conflict processing and social cognition in tasks with infants. We also have Dimitrios Askaidis, a postdoc in the same lab. He is also now with the Technical University of Denmark, who is a research software engineer and a mathematician, and has been involved in creating the pipeline for data analysis. And Velisar Manea, also a postdoc in the lab, who's been building his own pupillometer, and I'm imagining is going to tell you a lot about that. So this group have really been working out what is optimal for pupillometry with infants, with commercially available eye trackers, implementing a more optimal setup with their own device. I think this is going to be incredibly exciting, and I'm really thrilled that you could all be here with us. So I will let you carry on. Who's going first?
It's me.
All right. Welcome, Emanuela.
Thank you, Natasha. And thank you, ICUS, for inviting us to host this webinar. We're really happy to be here and talk about infant pupillometry. Also wanted to say thank you to Podium Conferences for helping us organize everything. All right, so our target audience for this webinar is researchers who may not have any experience running pupillometry experiments themselves, but who may have access to an eye tracker in the lab. So with that in mind, our plan today is to cover the basics of what the pupil response measures, and then we'll walk through all the steps involved in designing a pupillometry study, collecting the best data possible, as well as some recommendations for pre-processing pipelines and data analysis. That being said, we don't plan to really give any specific numbers around things like sample size, the number of trials you should include, or the length of a baseline period, for example. Rather, our aim is to provide you with enough background information such that you can make informed decisions around these parameters yourself. Now, for those of you who may be more experienced with pupillometry, we'll end our talk today with some discussion around what we think the future of infant pupillometry might hold, and our ideas for how to overcome some of the inherent difficulties in working with young infants. Now, if any of you have some ideas, please put them in the Q&A. We'd be really happy to see those and also discuss them if there's time. And before I continue, I just wanted to let you know that we'll have a blog post. We're working on that right now. That will be posted on the ICUS blog. And there we'll have a list of all of the resources that we talk about today, as well as a summary of our discussion. Okay, so let's begin with what the pupil response measures and why psychologists and cognitive scientists have become increasingly interested in changes in pupil dilation as markers of cognition. So to understand this, I thought it'd be helpful to start with some really basic anatomy. So the pupil is a small circular opening at the center of the iris, which is the color part of the eye. It normally appears dark or black because the inside of the eye is dark, not because it has a black opaque surface on top of it. Now, the size of the human pupil varies widely depending on lighting conditions, age, individual differences, tonic arousal state, etc. But under typical indoor or moderate lighting conditions, it tends to have a diameter around 3 to 4 millimeters. In very bright light, it can constrict to 1.5 to 2 millimeters. And in dim or very dark environments, it can dilate to a diameter of 5 to 8 millimeters. Now, one thing to note is that the pupil is constantly moving. This is a phenomenon known as pupillary hippus, and this is thought to be related to autonomic nervous system activity. But for this reason, it's not so meaningful to think of the pupil as having a steady resting or normal size. Now, the size of the pupil is controlled by two sets of muscles in the iris. The sphincter, or the constrictor muscle, which is depicted in green on the left here, is a concentric muscle that encircles the pupil. And when it contracts, it tightens the inside of the iris, which causes the pupil to constrict. The dilator muscle, which is depicted in yellow on the right side, is a radial muscle. So it's like spokes on a wheel. And when that contracts, it pulls the inner walls of the iris outward, which causes the pupil to dilate. Now, importantly, both the constrictor and the dilator muscles are smooth muscles. Now, I mention this because smooth muscles, in contrast to skeletal muscles, constrict very slowly. So smooth muscles are also found in the gut as well as in blood vessels, and they work very well for making repeated movements with low energy requirements. So they don't fatigue like skeletal muscles do. However, they are very slow moving. So even the fastest movement, which tends to be constriction in response to bright light, takes place over hundreds of milliseconds. So this means for pupillometry studies, you need to allow enough time in each trial for any pupillary response to unfold. This is also important for interpreting the pupil data that you might collect, because if you see large changes in pupil size that happen really quickly, they may not be due to contraction of the muscles that control the pupil size. Instead, they may be due to movement of the eye or other artifacts. So we do have skeletal muscles in the eye, the ocular motor muscles. So these are the muscles that can control movement of the eye, and these can contract much more quickly. Now, the pupillary response, both constriction and dilation, is primary involuntary and controlled by the autonomic nervous system. I won't go into the details of these two different pathways, and I included this review, or this figure, from Sebastian Matteau's review paper to illustrate that the neural pathways involved in constriction and dilation are distinct. Of course, they do interact. Now, just very briefly, the constriction pathway is depicted on the left, and the sphincter muscle that controls constriction is innervated by the parasympathetic nervous system. And this is generally involved in maintaining homeostasis, that is, keeping the body in a stable condition. This explains why pupils are generally quite small at rest. The constriction pathway is activated by a number of different factors, including bright light, near vision, as well as accommodative convergence, which is the process of focusing the eyes on a near object. So overall, the parasympathetic constriction pathway is important for maintaining optimal vision. By contrast, the dilator muscle is innervated by the sympathetic nervous system, which is involved in alertness, arousal, as well as the fight or flight response. The pathway is activated by also a number of different factors, including low light, far vision, emotions such as fear and anger, as well as stress. So overall, the sympathetic dilation pathway is important for maintaining optimal vision in low light conditions. But in addition to its role in vision, this pathway is also thought to be involved in regulating alertness and arousal. So studies have shown, as we'll discuss in a couple of slides, that the pupil dilates in response to arousing stimuli, such as loud noises, as well as unexpected events. And when we consider the subcortical structures involved in this pathway, this makes quite a bit of sense. So one such region involved in the sympathetic dilation pathway is the locus coeruleus, or LC. This is a small region of the brain that's located in the brainstem, and it's involved in a variety of different functions, including regulating arousal, attention, mood, as well as learning. It also contains neurons that produce the neurotransmitter noradrenaline. And release of noradrenaline by the LC is thought to increase attention and alertness. We now have some direct evidence from animal studies that activity of neurons in the LC mirrors dilation of the pupil. So for example, in a study of macaques by Yoshi colleagues, found when LC neurospikes are aligned to pupil dilations, this is the red trace, and constrictions, which is the blue trace. The example neuron here shown here exhibits a higher firing before pupil dilation and decreased firing before pupil constriction. Another region involved in the dilation pathway is the hypothalamus. And one very recent study from June of this year by Gruzic et al. With mice found a causal link between activity in orexin neurons in lateral hypothalamus and pupil dilation. So here are the findings from just one of the experiments in that paper, which shows an example pupil response of one mouse to stimulation of orexin neurons in the lateral hypothalamus across different frequencies of stimulation. So the duration of the stimulation is the green shaded area. And you can see that the pupil size increases during this time and begins to decrease when the stimulation stops. Interestingly, the same orexin neurons that code for arousal might also code for reward states. Okay, so throughout, I've already mentioned different kinds of pupil responses, but here they are explicitly. So the first kind of pupil response is the pupil light reflex, which is constriction of the pupil in response to increased brightness or relaxation of the sphincter muscle in response to darkness. The pupil response to light is generally quite quick and can yield large changes in pupil size. So as I mentioned before, in very low light conditions, the pupil can constrict to 1.5 millimeters. In bright light, it can be as large as 8 or 9 millimeters. The second kind of response is the pupil near response. This is a reflex that causes the pupils to constrict when focusing on a near object. And of interest to us, probably, or many of us, is the psychosensory pupil response, which is a dilation of the pupil in response to arousing or mentally demanding stimuli. It's also sometimes referred to as arousal-related dilation or effort-related dilation. Now, just to repeat, the PPR is thought to be mediated by the autonomic nervous system, specifically the sympathetic nervous system. When the sympathetic nervous system is activated, it causes the release of adrenaline and noradrenaline, which causes the pupil to dilate. Now, relative to the pupil light reflex, the psychosensory pupil response is much smaller. So in lab studies, generally you see changes that are less than 0.5 millimeters or 0.3 millimeters. In many cases, this relative change can be even smaller. So just something to keep in mind. So the PPR can be further divided into two categories of response based on their dynamics. So this is, of course, assuming that luminance or light levels remain constant. The first is the tonic or the state evoked response, which is a slow, sustained change in pupil size that occurs over a longer duration. Tonic pupil size is thought to reflect a subject's arousal state in the same way that heart rate or skin conductance might. Now, studies with infants have looked at changes in pupil size in response to viewing emotional stimuli, for example. Robert Hepak has done a lot of work that has looked at changes in tonic pupil size in infants and young children during helping scenarios that unfold over several minutes. In our lab, we often look at whether pupil size changes over the course of an experiment as a measure of alertness and attention. So rather than looking within a trial, we look across multiple trials and see if pupil size is generally getting smaller. If this is the case, this could indicate that attention or alertness is also dropping. The second type of PPR response are phasic or task-evoked responses. These are more rapid relative to tonic changes. They're transient changes in pupil size in response to a specific stimulus or event. Again, phasic changes in pupil size are thought to be a result of activity that originates in the LC and release of norepinephrine. So one thing to keep in mind is that although phasic responses in the pupil are more rapid than tonic responses, they're still quite slow. So changes begin around 400 milliseconds post-stimulus in adults, and it seems to be even longer in infants, so around 500 milliseconds at least. And this is when changes begin. So as you'll see in a couple of examples, usually peak dilation is even later than that. And again, this is related to the physiology, the smooth muscles. Whoops. I can just show both here. So with respect to phasic responses and cognitive influences, there are now more than 400 studies in adults that use pupil diameter as a measure of cognitive or mental effort. These studies began in the mid-60s or so, the first of which was by Hessenpolt, who measured pupil size as adults were solving easy and hard multiplication problems. And what they found was that the pupils dilated more for difficult math problems compared to easy ones. Around the same time, Kahneman and Beatty also showed greater pupil dilation in response to increased cognitive load. So in their study, participants had to memorize digits, and they varied the number of to-be-remembered digits. So in line with Hessenpolt, they observed that pupil size reflected the number of digits that had to be memorized. So although not all findings from early pupillometry research have replicated, these particular findings that relate dilation to cognitive load have replicated and are quite robust effects. So for example, we have also replicated them in the lab in individuals. So we've tried out the Hessenpolt paradigm ourselves. And what you can see here is the change in pupil size for easy and hard math problems for two of us. And this was only in 10 or so trials per condition, I believe. So you can see the effect is very obvious. And we often use this math paradigm to check if our eye tracker is working as a sanity check. But I think these plots are also a nice illustration of the time course of phasic or task-evoked response. So you can see in both plots that the pupil begins to react around 400 milliseconds, but the peak difference is quite a bit later, or peak dilation is quite a bit later. Okay, so moving to infant pupillometry. In contrast to adult studies, infant pupillometry is fairly new, but there seem to be around 100 studies or so now using this method. So there are quite a few nice reviews on this topic. I've just listed a few below. And one very recent review by HEPAC, it's in press, but preprint is online. It's going to be a book chapter. HEPAC categorizes infant pupillometry research into these two categories. So the first types of studies look at surprise or a violation of expectation. So this is the viewing of unexpected events which elicit an attention response, which then results in greater pupil dilation. These studies follow the same logic and design as looking time violation of expectation studies. There's a second category of designs that what HEPAC calls task-evoked response and neural activity. So these changes in pupil dilation are interpreted as markers of neural activity without necessarily invoking a response such as surprise. So in some ways, they're a bit broader than the VOE designs, but VOE designs are, of course, evoking a neural response. Change in pupil size is time locked to a stimulus or event onset in these task-evoked studies. So I'll just walk through a couple of examples of how pupillometry has been used in infants. The first example is one of the first studies that used pupillometry with infant participants, and this is by Jackson and Sarah from 2009. So this was a violation of expectation design, and here they showed 8-month-old infants physically possible and impossible events. So they'd had a train that ran around this track, and in the physically impossible event, the train would go through the tunnel and come out a different color. So what they found very briefly is that 8-month-old infants showed greater pupil dilation when viewing the physically impossible events. So they also measured looking time in the study, and what they found was that pupil dilation was more sensitive than looking time in the sense that it was less susceptible to the trial effects that you typically see in looking time studies. Another example of infant pupillometry study is this one by Caldy and Blazer from 2020. Here, they investigated the role of cognitive effort in infants' visual working memory. So they used pupillometry as a measure of cognitive effort. So what they did was had 13-month-olds in a delayed match retrieval paradigm, and they looked at both their behavioral and pupil responses. What they found was that infants who had larger pupils during a memory encoding phase of trials had better subsequent memory performance. And this was at both the group and at the individual level. The relationship between pupil size and performance was also present on a trial-by-trial basis. So trials in which pupil dilation was larger during encoding were more likely to end in success. And then I'll just briefly mention a study that we did. So this was more in the domain of social cognition. And here we had 18-month-old infants, two groups of 18-month-old infants in a belief-based action prediction type scenario or perspective tracking scenario. So here you see our stimulus video, and the swarm of different dots show the gaze patterns of the infants in our studies. The two colors represent the two groups of infants. So we used a between subjects design here. The two groups specifically were 18-month-olds that recognized themselves in the mirror and 18-month-olds who didn't yet recognize themselves in the mirror. And we were interested in seeing whether we could use pupil as a measure of conflict, specifically when self and other perspectives diverge. And so what we found was that it was only the mirror recognizers that showed greater pupil dilation during the anticipation phase of our stimuli compared to non-recognizers. So indeed, it seemed to show that it was the mirror recognizers that experienced this conflict. Okay, so maybe you noticed from some of the studies that I just ran through very quickly that in contrast to the math studies or the working memory load studies, the stimuli that we use or the things that we present to infants are quite different from how pupillometry has been done with adults. So with infants, we can't give them any task instructions. We can't have them stare at a blank screen where we can control luminance completely. Rather, the stimuli that we use are typically dynamic and involve a lot of gaze shifts and eye movement. And for many other reasons, infant pupillometry can be very tricky. So as Hepak really nicely says in this book chapter, at any given point in time, pupil dilations can be the result of many things. For example, luminance adaptation to the environment or the stimuli on the screen, visual field and focus. So if you imagine an infant who's moving constantly, the visual field of focus or the field of focus shifts a lot as well. There can be eye and head movements, changes in tonic arousal state, as well as psychological engagement. So if we're interested in measuring these small changes that are due to cognitive influences, how might we best design our studies to accomplish this? So this is what Balasar will now share and discuss. Over to you.
Okay. Thank you. Give me a second. Okay, yes, there's right. So actually, I wanted to start by talking a bit about how eye trackers work. We ended up building something like that. By the way, it wasn't only me. It's with my colleagues here and some other people outside. But initially, it was just that we wanted to understand what we're doing. And as you probably know, you understand by doing somewhat better many things. And let's sort of open up the mystery of the device, if possible. They are actually quite simple devices, as some of you probably know. And I'll go through a very basic walkthrough of how these things work. You'll see, hopefully, why some of this the data is relevant or could be relevant. So, for example, we'll start by talking about how the image is acquired by the device, and then we get into the algorithm. Then we need to write some of the data to disk, the data that is interested to us, to get it to analysis. And I'll also share some extra considerations about device types. Now, what one needs to have is usually in most modern eye trackers or dedicated eye trackers is a source of invisible light, which is near infrared light, and the camera, which is with a sensor that is sensitive to that light, and probably also with a filter that blocks the natural light. Fortunately, most modern sensors, digital sensors, CCDs and CMOS sensors, they're all somewhat sensitive to infrared light. So this is actually quite simple to know. See that this is not a fully full screen. Just a second. I hope it doesn't bother you that my that you can see this. Okay, all good. Now, what we want to, I mean, as you can see now, the 12-month-old is looking, is paying attention. We need to end up with an image that is as clear as possible for the algorithm, because the algorithm basically has to detect some circles. So if we removed all the visible light, we won't have any reflection in the eyes, as you probably know. But that's why, and also the small white blobs are the reflection of the corneal reflection, the reflection of the infrared light, which is then used to, especially for eye tracking, because it doesn't shift position. It's usually fixed in place. And then the actual image acquisition is another step where the sensor is read and is placed into something like a buffer where the algorithm can work. Now, what the algorithm does is that it obviously searches for pupils, and the fact that you may have heard that we get pupillometry for free with any eye tracker is that it's a stage before figuring out where the subject looks. This stage of finding the pupil and finding the center of the pupil. I don't know if you can see here the distance between the center of the pupil and the white blob changes if the subject looks around, and if this is mapped to the stimulus space, this is basically eye tracking. So in this pipeline, some eye trackers, especially those that we use to install this with babies, not all of them though, they have a marker on the face. The marker serves two important purposes. One of them is it's very easy to find a high contrast feature for the algorithm, and the other is that we always know the size of like a print. So we can figure the pupil size in millimeters directly. And then once we know the size, the algorithm can figure out where to search in a large image such as this one. Also then you can limit the search by specifying what kind of circles you're looking for. And yes, then you look for the usually the white blob that is closest to the center of the pupil. So with that out of the way, let's take a quick look at the debug image, which may help us understand why sometimes the tracking doesn't work correctly. So here we can see this particular implementation of the algorithm looks for concentric circles, but the algorithm also found many other potential candidates, feature candidates in the drawings of the baby's pajama, the baby's nostril. So it is ideal when it has enough data to limit the search to the eyes once it found a different pupil. Of course, there are many different algorithms, and there are much cleverer ways to do this. But it's a constant issue that the machines don't see the world as we do. They don't have the pragmatics. Okay, moving on to writing data to disk. Well, the question is what data is important for us. And many of the data can be but we kind of need always an exact time of the frame. We need to be able to get an exact stimulus time or quasi-exact that we can give if the eye tracker application presents the stimuli if it's built in. If not, we need it from the application that presents the stimulus. We obviously need the pupil size for pupillometry, and different eye trackers use either diameter or area or both. Interestingly, some algorithms have this compound measure of confidence, where it helps you to understand if confidence, how good the guess is. This is quite useful to find bad data. And then later on in the pipeline, the case coordinates. And in some cases, in some academic projects, the actual image is saved to this. This is the largest chunk of data, but it's quite useful because you get a very good understanding of what is happening there if you can review the images offline. Unfortunately, as of now, I don't know any commercial product that does this because they're mainly eye trackers, and they recorded very many images per second. So it would be very, very hard to do. And the final data that we want to reconstitute is something like that. We want to know the exact time, as we said, when this frame happens, what was happening in the stimulus. We want to know if so in this marker-based algorithm, that the marker was found, that the pupils were found in the correct ways, and it's actual eyes, and the reading of the pupil is the pupil and not some noise or some low contrast pixels in the iris. And of course, we want to know where the baby looks, not only for eye tracking purposes, but it could be that the luminosity of the zone of the images can also influence the pupil size. So that is quite informative, actually. All right. So quickly, you may have noticed that I've talked about remote eye trackers so far. So most labs used to have this kind of trackers where you put the eye tracker below a screen, and you have the subject sitting in front of the screen. This does require this notion of a head box when you're doing studies with infants, which is sort of the frame of the image where the infant can move around, but it's a box and not a plane, because infants don't move around in a plane, and they need to be able to track to find eyes in this virtual space in the real world. And it's kind of a brute force approach because obviously most of look at this image of myself. The pupils are very small. If I'm moving around like an infant, then you need quite a large head box, and that's kind of always the problem, that you need high resolution and high bandwidth to do this. And because infants also move forwards and backwards, sometimes a focusing mechanism would be quite useful if we don't see that. Also, if the subject is very far from the eye tracker, the infrared lamp needs to be quite powerful. Head-mounted eye trackers, on the other hand, don't have any of these problems. You can place a camera very close to the eye. You can have a low-quality camera and a low-power infrared light because almost all the pixels are occupied by the pupils. The problem is that with infants, it's kind of hard because it can get uncomfortable. Because if you see their eyes, they see your eye tracker, and some infants, quite many, tend to mess with it. The other problem is that it's harder to use with mixed methods, because if you have an EEG or a FNIRS helmet, then it's harder to, on top of it, to waste the time and position the eye tracker. Okay. So with these considerations, let's talk a little bit about experimental designs with babies. Again, as Emanuela mentioned, we're not going to give you any rules and fixed numbers. But there are some things that are specific to pupillometry that are different even from eye tracking, let alone the other methods that we used. And I guess you should be aware of them, basically. So the main thing is that there are many things that are not signal, in the sense that signal is something that is of interest to you. So the main thing, obviously, is luminosity. If pupils react 10 times more to luminosity than any cognitive effect, then it is the main issue, and we'll come back to that. Eye movements also can introduce distortions. Fortunately, these are short. These distortions are due to the fact that pupil material and iris material is soft. Pupils are not a piece of material, as someone said. And also because the camera has an exposure time, and it can just get you can just get the motion blur. Right. As I alluded to, the area in the frame that the subject is looking at can have darker or brighter objects, and they can introduce changes in pupil because of that. And that's also that's kind of a problem, because it always depends on the setup, on the size of the screen, on the brightness of the screen, on the distribution of these objects, and so on. Another consideration is that since these muscles are slow, the pupil response is easily the interesting part should be after the first second mark, as you can imagine. If you get a strong signal before that, you should be quite suspicious. And all the other classes of issues where the guess of the algorithm is wrong. I think modern eye trackers are also correcting for this effect, which is well, any circular opening is circular when it's facing you directly. Of course, if you it becomes an ellipse if you tilt it. So if your setup uses a large screen and infants look around it, the pupils will become quite elliptic. The issue is that it's not quite that simple. It could be that because there's basically a lens before on top of the opening, in extreme angles, this also diminishes the surface area. It's not only oval, but it also changes or deforms the diameter. So not only the area. So for brevity, let's try to see if we want to adopt a looking time design to pupillometry, what kind of things we should pay attention to. So on the bright side, this is time series data. It's quite different from what you get in a looking time experiment, where you're interested in the outcome part. There's a difference between your conditions. You can look inside the trial, and that's, I guess, one of the main allures of this technique. On the other hand, these designs tend to be a bit more rigid. If you look at adult literature, they're really rigid. With babies, we cannot do this. So, for example, if baby move freely, the pupil size will just vary as a result of their changing distance to screen, because the pupil is projected on the sensor as larger or smaller. But I think modern eye trackers that have a headbox correct for this. The larger problem is that while a good practice in adult pupillometry studies is to match the luminosity of the screen with the luminosity of the room, with infants, we throw everything at them to pay attention to our stimuli. So usually you use a very dark environment and one screen and nothing else, which means that the screen is the only source of light. So if they get closer to the screen, the pupils will contract proportionally. So we said that we won't give you numbers, but here's a number. So usually to get the best pupil dynamic range in movements, it would be best to have as much dilation and constriction possibilities around some mean. So I just thrown here this 5 millimeters pupils that would be just between 2 and 8. That's something to keep in mind. You can try it in piloting. Of course, there will be quite large individual differences, but it's something to keep in mind. Also, not to worry too much, because if the pupil sizes will turn out to be around 3 millimeters, then the subject's eye hurt. And if they are close to 8, then they don't see much. But something to keep in mind. Right. So the other big issue is this changes in stimulus luminance, especially with more naturalistic looking stimulus. So you would get over time a difference in pupil light reflex. And the fix is this recommendation of making isoluminant stimuli. So here's an example of something we did. This is much easier to do if you build your stimuli from scratch in a 3D environment. But you can already see by the muted palette here that we did this, so different events in the movie don't have differences in luminosity. The way you do it, when you build your own stimuli, you can sample the images and place the light so that they are constant from one part to another. But you can do this with video if you're shooting in a studio, or you can do it with video by controlling the exposure of the light. And of course, for many of the infant stimuli that are very simple abstract shapes, then it's very easy to measure the light of each feature. So this is something to keep in mind, but it's not absolutely obligatory. And here's why. This is an example of raw data from a study where we had 4 conditions per infant. The conditions are of course different, so different things happen inside of them. So we try to limit the differences between conditions by aiming for relative isoluminance, but what is important is then, of course, you can see here that different things happen in different parts for different conditions. But if there's some similarity in the displays towards the end, and this is normal for most good experimental designs, the outcome is constant and so on, pupils tend to converge. So if you cannot aim for isoluminance, then it's good to have the same event before the measurement period. One other problem with this is that if the action, if babies look outside the screen for a little bit and they're in the dark environment, then of course there's a problem because there will be a huge dilation. And so from here, for example, this ball exits the screen a little bit, then comes back. And we had an issue when we were doing this in a dark environment. So one idea is to just use a gray bar of the average luminosity of your stimulus. Yeah. The other thing that is quite important, I guess, it's this idea of baselining. So here you can, I guess, coming back to the point of time series data, the people always changes. And here are 6 trials of the same subject, which is me, during a day. looking at a very simple pupil light reflex experiment. So they vary a lot, but there are some patterns. And if you want to compare different subjects, you would want to be able to match those things. So we're interested in relative change, so we want to have this baseline to see if the pupil contract or enlarge in the period that we're interested in. Now, some general recommendations would be that, for example, this segment should be short because we don't want to average out a lot of data, and people in the in the infant literature are using something like half a second. It's good if the baseline isn't at the point where the pupils tend to be very large or very low, because again, we want to maximize dynamic range to detect an effect. And we can use, if there's a portion, for example, like this or here, we can use something like a medium variant or more clever things, of course. And then we average between subjects, and then we have one line. One other consideration is that it's preferably close to the part that you want to measure this baseline. So if the baseline is at the beginning of the trial, maybe different processes were involved. So we're averaging on something that is quite different, given that pupils are influenced by so many things. All right. So the other thing is that this is especially important between subjects, of course, because they are different, because they have different pupil sizes. Within subjects design, we may not need to baseline. So the thing is that over repeated trials, there may be some drift, and then you can model the drift with some statistical approach to it. Also, it could be that you sort of get lucky, just because we are interested in the same subject reacting to different things. Let me actually show you what I wanted to do. The same image that we had here is that you can try piloting to see if the stimuli that you build are good, right? And you can adjust the timings of the events. That's all I have for this part. I'll let Dimitris to tell you more fancy stuff.
Oops.
Okay, all right.
Yes, hello. So continuing from the experiment design, we go to pre-processing. What?
Yeah, good.
Yeah, something happened. Can you? We go to pre-processing. And the pre-processing is very important. In a good pre-processing pipeline is what will take us from this to this, to cleaner data, so that we can use for our analysis. Pre-processing is very important in pupillometry because, as also the previous speakers have mentioned, the pupil data very usually contains certain artifacts that can be blinks, it can be other partial occlusions of the pupil or eye tracker noise. For example, subjects are harder to track while they move, and that's especially important with infants. Standard pre-processing steps that most pipelines include is removing bad samples, which is missing and extreme values that are out of normal physiological bounds. Samples that are around blinks that usually are influenced by partial occlusion of pupil, and different types of deviating samples. Then interpolating missing values, usually up to some length of gaps, consecutive gaps, smooth using some low-pass filter usually, data from each eye, and average the time series of each eye into a mean average pupil time series in a smart way. And a good rule of thumb is that 2 eyes recording pupil data from both eyes is always much better. We can get much better data quality than from 1 eye. And here I will describe the one that we use in our lab, which is a pre-processing that's adapted from CRET and SIACSIA. And I like also this pre-processing pipeline because it offers some sort of visualization of the pupil, of each pre-processing step. And we see here, for example, we have the original data, which are these squares from both eyes, the green and the red one. And we go from this data that contains all these blinks. We get this yellow line, solid line in the middle, that is the average data, and it's clean, doesn't contain any blink. So the first step that we do actually, and this is some small tweak to their pipeline, is that we remove the data from 1 eye if it's quite worse than the data from the other eye. So we check it by comparing the standard deviations of the time series of the 2 eyes. And if one is quite bigger than the other, then we remove that eye from our data completely and just pre-process the other eye, because it's gonna make our final data worse. And there are also other ways to work with it. For example, you can check how much data is missing from each eye. But most of the times, both eyes are good. But sometimes it happens that, for example, irises do not have the same color exactly, and you can have a higher contrast in 1 eye than the other. So the eye with lower contrast can be harder to track for the eye tracker. And the next step is removal of outlier values, which is done in 3 sub-steps. The first one, as we mentioned before, is removal of data that is out of normal physiological bounds. And we see here, and usually this data is around blinks. So around blinks, eye trackers can get quite confused either by partial occlusion or by the partial occlusion of pupil. And so we see that this above some values below and above the bounds will be removed. The next step is a dilation speed filter, which basically controls for the speed of like the difference of 2 consecutive samples. We have said already that pupil dilation is quite slow process. So this filter removes data that increases or decreases too fast, too suspiciously. And this pipeline uses some threshold which depends on the median absolute deviation of the data. So we don't use a specific threshold for all subjects essentially, but this depends on the data itself, which is good because some subjects have data that is more noisy than others. And here we see, for example, this is a blink, and we have missing data here, and we see that due to partial occlusion of the pupil, the pupil size decreased, but this is artifactual. It's not that the pupil size really decreases. And this data is removed because the decrease of the data is too fast. And the strength of this step actually is that it's also good for detecting half blinks, which we had trouble when we were setting up our pipeline to detect initially with other tools we were trying. For example, we see here, this is a half blink. This is partial occlusion of the pupil that doesn't lead to the pupil disappearing completely. So the tracker can still track something, but it's not the whole pupil. And we see that the data is decreased. So we don't have missing values so that we can detect this blink. This filter detects and removes the artifacts from this sort of artifacts. And that's weird. And then the other step is this smooth trend line deviation filter, which basically creates some sort of trend line for the pupil, and it removes samples that deviate from this trend line. For example, from the previous filter, we have this lone sample here that stayed and that wasn't removed before, and now it's removed because it's very far away from the other samples and doesn't follow the trend line of the other samples. And this we can apply it for a number of times to remove consecutively more and more artifacts. And finally, there is removal of islands. So there are some temporally isolated samples that because maybe they don't change that fast, and maybe because they're clustered together, they don't get detected by previous tests, but they are isolated from the rest of the data. So this step removes this. These are usually artifacts from the eye tracker. So after we have removed all these outliers, we continue to improve the data that remains to improve the quality of it. And this is done by interpolating gaps. So usually this is mostly blinks. We don't want to lose this data. There is no reason to lose it, because also pupil size will not change much around this in this small amount of time. You can choose which length of missing data you want to interpolate, up to which length. As some people just interpolate everything. Some people, like, we choose to put 400 milliseconds because that's usually catches all the blinks of a baby. Babies also have a bit slower blinks, I think, than the adults. Adults are usually between 100 and 200 milliseconds, but babies, we see in our data that they can blink for longer. And just to say also that any number that I present here is just indicative, and we tested a lot of different values to come up with a pipeline, and that's what we recommend also for people to do to test their setup. It has a lot to do with the specific eye tracker you use, the sample rate, and with the populations you study. So don't take any of these values as recommendations or literally. I would say that, yeah, test your own setup and try to see what works for you. And finally, then smoothing the data with a low-pass filter. So we use a 4 Hz filter because there was this argument by Jackson and Sirois that data above that in higher frequency components, we observe less correlation between pupil between the two eyes. So basically, data in higher frequency components has more noise to signal ratio. So it's better to remove it to have better quality of data to analyze. And finally, here we see how it looks, how the data looks after the smoothing. And finally, we average the two time series from two eyes to get some mean time series. This can be done with a simple way of just averaging the values at each time point, but there are also more sophisticated ways that basically model the mean pupil size. They create some mean pupil size that's basically a model predicted by the two other time series. And in this way, we can actually have a good prediction, a good estimate of the mean pupil, also while we have missing data from one eye. Because for that time period, the tracker just lost the track of one eye, but it had a contact, still it was tracking the other eye. And this was the pipeline. Then there is also another consideration for those who use iLink and some other eye trackers, maybe, that we may need to convert arbitrary units into millimeters. And this is useful because, I mean, it's good to be able to compare the results between studies, of course. And this is actually simpler than it may look like. So the idea is that, like, very simply, you can print fake pupils at some different sizes. For our setup, we printed at 3 different sizes. You see in the right hand side of the screen the different pupil sizes that we printed. We also printed that grid to make sure that the printer was accurate, was not magnifying things, and we had a good, we could be sure that the pupil size was what we were really expecting to be. Then you can put this piece of paper basically in different distances from the eye tracker that are basically, these distances are what you expect the baby to be. And record some data for each combination, and then compute which parameters create the best fitting model for predicting your the absolute pupil size in millimeters by creating a linear model with which contains the arbitrary units, the distance from the screen, and some constant parameters. And for us, we saw that with our iLink setup, we got some values for this, and these values are what we use. And yeah, and there are some resources from iLink, but the resources don't really involve remote eye trackers, so you have to adjust it to that. There is also, because typically glint, the presence of glint is required for pupil tracking. You can either remove it programmatically from the settings in the iLink host computer, or you can actually print the glint on the pupil and it will just detect it. That's what we did. And we move on to, finally, after we have cleaned our data, there's also the process of determining which trials we include and which subjects we include. And for this, I would say there are no strict recommendations in general, but aim for something that makes sense for your data. And in our experience, data quality is more important than amount of trials in general. And the thing is that usually what we see is that babies that have too few trials, usually also the trials that can get included somehow, they have bad data. So in our experience, it's in general less about requiring 2 trials or 3 trials to be able to detect an effect, but more important is the quality of this trial. So usually having a threshold of 2 or 3 trials, it means that the babies that get accepted also have good quality of data in general. And I will have some more general procedural recommendations to that. Preprocessing is quite important, and it's quite important to have a very quite clean and preprocessing script that you can use for multiple data sets, and separate analysis and preprocessing scripts, because analysis, you're going to adjust it to each experiment design. But preprocessing script, it's a good idea to have it ready to use it for any study you're gonna do. And use one of the standard pipelines for cleaning up a preprocessing pupil data and understand what the code is doing. Like we had this issue some point in the lab that we were using the same pupillometry package, but we were getting slightly different results just because we were using different versions that were handling missing values in different ways. And well, until we figured it out, we were getting a bit crazy. And here are a list of pipelines that we will also put in our blog. If this is just an indicative list of some pipelines we have checked or we have seen, but if you have some favorite pipeline that is not included here, please write in the chat and we can put it. And then after now we have our data clean and nice, so we can analyze it. And a very standard and classical way to analyze data is to average across some time window. So you can say that you have some outcome phase or some encoding phase and or whatever in your experiment, and you want to analyze the data in that time window. So you average, and this way you reduce noise a lot. It's an easy to do analysis because you can just run a t-test or an ANOVA test after, and yeah, you can. It's quite robust analysis in some ways, but you lose all temporal dynamics, and you have also the risk of washing out effects, especially if you don't have very exact predictions of the very specific time window that your effect may be. So you risk of making your window either small and missing the effect, or making it too large and washing out the effect, because the effect is going to be in some part of the time window, and in the other part of the time window is going to be no effect. So it may be if you don't have enough power, maybe you don't, it's less easy to detect it. So question is how can we have some benefits of the window averaging and still have some temporal dynamics and flexibility in our analysis? And one solution is to time bin our time window and analyze each bin separately. So this allows us to be more flexible and be able to detect an effect that is in some part of the time window and not in the whole time window if the time window is too large. But if we use multiple bins, we run in multiple comparison issues. So the solution, one solution that can address these issues is using functional data analysis and control multiple comparison issues with permutations. Functional data analysis is a quite modern and flexible way of analyzing data. It was first used, I think, in pupillometry by Jackson and Sirois. And this way, it allows us to get to keep quite much of temporal information from the pupil type series. It may have some disadvantages, some specific cases, if there are some results that are kind of sustainable through time, but there is a lot of local noise. That's why it's quite important to low pass filter the data before using functional data analysis, unless we use long enough bins. And how functional data analysis work? Basically, you compute a t-value at its time point of your experiment or the time window that you said that you want to analyze. So that it's sort of like running a t-test at every time point or at every bin, but you don't exactly run a t-test because you just produce a t-value and that doesn't tell you you don't make any inference from that alone yet. So you have basically a t-function instead of t-values. And then you permute the data. So for example, if you have two conditions, you just randomly shuffle these two conditions at the subjects. Or if you have between subjects analysis and two groups, you can shuffle the group membership randomly. And then after you permute the data, for example, you do the same procedure and you compute t-values at each time point for this permuted data. And you repeat and you compute permutations. So you keep computing permutations and computing t-functions for each permuted data. And then you can check how many permutations give you higher t-values than your original data. For example, we see here in the plot on the right, we see the t-function computed from the original data in red. And we computed also 40 permutations. So the t-functions from these permutations are with the dotted blue lines. And we see that the dotted horizontal line is the maximum of our original data. So the equation of the t-function of the original data. So the question then is how many of these permutations are above this line. So one could say that if less than 5% of permutations are above this line, then we have significance. So you basically compute null distributions and then check with these maximum values. And as we see here, actually, this is one issue that we can have this data if we are too if we don't make very clear, if we make too wide, if we analyze all the trial, for example, and not specific parts of the trial, we see here that there are a lot of permuted t-functions that get above this threshold in different parts of the time window, because we have put here our whole trial, for example. And this means that if we don't have enough power, if we have a lot of noise and the effect is not that big, if we put just all our trial there, then we get into a risk that just randomly we have t-functions from permuted data that exceed our the t-function of the original data. While if we see around the time window of the outcome in the right, we see only one of the 14. So the idea is that while this way of analyzing data is flexible, it still helps a lot if you are able to make some sort of prediction over where your effect is. You don't have to make, you can be still flexible and not be very exact. You can analyze 5 seconds and not make prediction if your outcome is 5 seconds, but it helps if you don't just put all your trial inside there. And there are different ways to actually control for that. You can use, so now what I mentioned was some sort of global estimate, global control, but you can also use cluster-based controls. So you can threshold your t functions up to some significance level for the t statistic and compute the maximum cluster for experimentation. And I have some code that I use for this type of functional data analysis that you may find useful if you want to use this type of analysis. And
You're frozen.
what? Oh. Sorry. And some other analysis methods that are more advanced and maybe a bit harder to conduct, but they can be very powerful if you basically design them well, is a growth curve analysis and generalized additive mixed modeling. So this can give you a lot of temporal information, much that from your pupil time series. Okay, sorry, we have technical difficulties here. I have to wait, sorry. Okay, thank you. Yeah, and some final considerations is, as we have mentioned before, a lot of pupil size varies a lot depending on things like which part of the screen you look at because of luminance differences. For example, it can be local luminance differences in different parts of the screen, different objects, or to different viewing angles, or just saccading around or looking up usually induces some increased pupil size than looking down. So I mean, in principle, this is just noise. And if you don't have systematic differences between conditions or between groups, it's just something that makes it harder to detect an effect. But if you have to make sure, if you find something that you don't have systematic differences and the result is not due to this difference. For example, here we had, like from one of our experiments, we had 2 conditions. In one condition, the ball goes into the box, and in the other condition, the ball goes out of the box. And we see at that time that the pupil size here is higher in the condition that the ball goes out of the box. One could say that there is something there, and maybe infants increase their pupil size because of that. But the thing is that that infants look closer to the outside of the screen, and outside of the screen it was dark in the experiment. So that was the reason actually that we see that there is a higher pupil size in the second condition. And actually we're able to analyze it. So we put as predictors both condition and the distance from the edge of the screen. And the distance from the edge of the screen was completely accounting for this pupil difference. And there was no affecting condition when we were controlling that. And now we're passing to Velisar.
Yeah, just quickly to see if I have something. One moment. Can you not move the mouse a bit, please? Mouse. Okay. Thank you. Right. So just to end up quickly with what we've discovered while trying to figure these things ourselves. So as you've seen, there are many things that can influence your data. Back to my design recommendations, this situation reminded me of this general recommendation of having the outcome or the actions close to the center of the screen, which of course is the case, but you may want to look, as we want in this experiment, to see of different parts of the data that may be interested, and you cannot always have them in the center of the screen. So we started to build this, well, we call it a system just because it's compatible with different cameras and different software. So it's like a framework in which you build the device for your needs. We wanted to get access to some things and to solve some sort of recurring problems, which I'll quickly enumerate here. So one problem is that you just lose a lot of data in some of these kind of experiments. You don't have enough good data. Babies become, you don't have good calibration. You don't know why you lost the data. So that was one of the main things that we also do, one of those systems where all the images are saved, and we can do a sort of a relive of the experimental session. And if we can do this, we can change the parameters of the algorithms, we can retry the calibration, we can do all sorts of things that you may not get right under pressure when you're doing the actual experiment. Calibration wastes time, the limited time, some of the limited time the infants have. So if we wanted to implement, and we're still toying with different ways of implementing very fast calibrations. We also have a calibration that doesn't actually exist. You just, when you know or you think you know that the infant is looking at a certain feature, you just click on that feature. And if you find two instances like this, then you calibrate it. And we wanted to maximize participants' comfort, because part of attrition is due to that, but it's not directly because of eye tracker misfiring, as it were. So this is why we opted, for example, for a remote eye tracker still, and for some other things that I'll touch on in a moment. And of course, since pupillometry has this enormous potential, we want to have as many experimental designs brought into pupillometry, and some new and imaginative in it. And as it is for adults, it tends to be quite rigid. So, for example, we are developing a system that compensates for the pupil light reflex. We cannot do it automatically for everything forever. I don't think there's a way to do it so it just works. But point is that an experimental design tends to have the same stimuli in the same on the same monitor, on the same layout. So it could be like the thing that you do at the beginning of the like a wizard, that you do a number of steps, and you can take the light of different features in the stimuli and map the relative luminosity in a pilot study, and have like a column of data that adjusts or compensates for the effect of these things. It's kind of the high level description of this. We want also to have the largest head box of any eye tracker, so infants can move a lot, and we can use large screens and weird layouts. We can do this by building a camera that tracks the subject around, so that we also don't waste pixels, because we're mostly interested in the eyes, or at least the face. And we also want to track several subjects, because we can have a caretaker or two adults at the same time in the image. Why not? We just need to run the algorithm twice. On top of this, since this was a learning exercise, we want to understand each step, and we want to have to get some feedback of what we're doing wrong, and what works and what doesn't work. So since we have the images, we can check the algorithm guesses, we can have this debugging access, we can tweak all the parameters, and we're using open source algorithms as of now. Some of them are quite modern and quite good. And we want to make it as easy as possible to check the system and the results of your study immediately. So there's an export function that gives you quite usable data, and you see what you're doing, and you can iterate the experiments. One general problem of infant studies is that you commit to something and you know after a year or two what you've done. And you want to be able to iterate like you do in, say, product development. Also, we want to be able to focus and adjust exposure in real time, because you lose data if the subject comes close to the screen, the pupils are blurred. So here's an example of a hardware prototype working in our labs in quite a wide space on a big TV. And a closer look, this is actually a different prototype. You can see that we have a follow focus, like people in the cinema business are using, and we built our own lamps because for larger distances and not custom built sensors, you need a lot of power. And ideally, we would want to end up with something like a control robot that has to access and tracks the subject around, and then you end up with only the eyes, as I said. And that's an illustration of what we can do now that we're, as of yet, we're manually focusing, but hopefully we'll get into, I don't know if you can see this, but the algorithm regains the eyes once the image is in focus. The autofocus should also not be a problem as hard as for a serious camera manufacturer, because if you have a clear reference, like if you only look for faces, or if you only look for a sticker, then it should be quite easy to find and to figure out the distance. And the main part of this so-called system is the software. So we have an application that controls everything. You can even run quick experiments in it. So once you fire up the eye tracker, you can design an experiment by just modifying a JSON file. You don't even need to know how to code. Of course, this won't be very sophisticated experiments. And then it displays the stimulus and the subject and the tracking either in real time, or you can replay it offline, frame by frame. And then you can rerun different parameters, which actually can show you here. You have access. We have access for now, because this is in development, to every settings if we want to, and we can tweak and change so that we understand what works best for a certain layout, a certain experiment. Yeah. This is quite interesting because if you're able to somehow anonymize the data, then you can see, like a peer reviewer could see your decisions, for example, or someone else, and can try different decisions. And indeed try different things on all data. And in some situations, this JSON file could be also part of the pre-registration, which, by the way, we have some ideas about how to do pre-registrations. It wasn't really enough to be part of the main presentation, but we're happy to talk about it in the Q&A. And that's kind of the idea with dual pupillometry. It's one of the few, pupillometry being one of the few psychological processes that measures kind of the same underlying physiological aspects. It is good since you have the parent there to just use the parent as control. Or imagine something like an A not B task, where baby's pupils dilate for revealing A empty and parents for B. So this is kind of new. As I said, in just due to many factors, some experiments tend to lose up to half of the data. Of course, this is not because the other sub-trackers are bad, but it's because, well, the screen is small, the situation is cramped, the calibration was long, and so on. And if we can systematically improve those things, we have a chance to get more out of this, and this is very precious data. And I mean, we are probably quite lucky, but after 30 to 34 participants, we have 100% of the data. So that's kind of the exciting deal. All right. So finally, I have to mention our hacker, Valentin. He did the software, and it's great how many iterations and how much he did in so little time. Also because we had all sorts of ideas that we had to implement. All right. And I'll leave Emanuela to end off.
Thank you. So we are going to wrap up here. So if you have any other questions, please put them in the Q&A so we can answer them before this ends. But we will also share our email addresses so you can email us at any point. Let's see. So I'm having trouble moving to the next slide for some reason, Belisar. Yeah. I think you can just follow here. I don't know, I can't control. But anyways, we hope we've given you enough information to maybe consider running your own pupillometry studies, even if you don't want to build your own pupillometer. We think pupillometry can be a really interesting tool as it allows you to measure the dynamics of a cognitive response to see how it might unfold over time. So why should you do a pupillometry? This is one reason. Another reason, which Belisar mentioned, is that the pupil response can be used across the lifespan. So there aren't so many measures outside of neural measures that allow you to do this. So looking time, for example, doesn't work with older kids or adults, but the pupil response does. Can you move to the next slide, Belisar? We think looking at change in pupil size can also be an additional measure of the cognitive processes that you might be interested in. So this could provide additional or converging evidence for your predictions or hypotheses. So for example, I've been using pupil dilation to look at conflict processing, but there are also, of course, neural regions that might also measure conflict processing. If we do studies where we look at both pupillometry and FNIRS, for example, and see similar response, this would provide us with more confidence that maybe we are measuring what we think we are. And then finally, how should you do a pupillometry study? Just to wrap up the many things that we talked about, consider, of course, the time course of the pupil dilation response when designing your stimuli. So the pupil dilation takes time to begin, and then the time course to reach maximum dilation also unfolds over several hundred milliseconds. Control for luminance to the best of your ability. As I mentioned before, the pupil primarily changes in size due to light, and changes to light are much, much larger, up to 10 times larger than changes due to cognitive effects. So control for luminance to the best degree that you can. There's a question about luminance, which I think Dim is answering right now. Consider how gaze and saccadic shifts may affect pupil size. So when we use dynamic stimuli with our participants, our young participants, think about maybe how that could change the pupil size in your measurement period. As Dim said, record from both eyes if possible. And it's also important to review your data closely during pre-processing to make sense of whether your pre-processing pipeline is working properly, but just to, in general, better understand your data. So we have a couple of resources here, but it's certainly not a complete list. As I mentioned, we're working on a blog post, so we will make sure to include all of the resources that you've seen throughout the different slides. And finally, we just want to thank you for your attention today. And our email addresses are here, so you can contact all of us, one of us. We're happy to respond to any questions that you might have. Let me just look in the Q&A now. Okay, yes, lots of questions coming in now. Okay, thank you. About the slides, yeah, I think we had planned to share the slides. we'll figure out with ICUS or podium conferences the best way to do that. They might just be posted with the blog post or something like that. But yeah, we're happy to share the slides. Yes, there are some interferences that happen with FNIRS and eye tracking. How do you test and prevent this? Yes, we have dealt with this interference before. So FNIRS, of course, uses infrared light. And as we've discussed at length, we also use infrared light for eye tracking. So do you want to answer the best way to test for it?
I mean, the best way to test for it is to, I think, like, or I don't know, like I mean, we tried to put some shower cap on top and it was kind of working, but it was annoying infants a lot. So we were losing the subjects because of that. So we are working on some better method to kind of cover its optode in some way. And the best way to test is to basically put some subject there and cover the infrared lamp and see if you see some difference in the pupil size. And now we use actually our Artemis system that actually detects if there is ambient light. So we can also use that one. But I would say that, yeah, with our Gaia Labs system, it was very obvious, at least when we had interference, because if we were occluding the lamp, we could see the frontal channels dropping. Yeah.
Yeah, so with our TINUS system and our Pupillo, because the participants are a bit further back, we don't really see the interference that we had seen previously. And with this system also, yeah, you can see that when you are putting the cap on and doing the calibration, the amount of ambient light. But yes, preventing it is difficult unless you can move the participants further away. Testing it, yeah, as Dim mentioned, you can have a participant, or you can, move the cap closer to your eye tracker, and it should be fairly obvious what the interference looks like.
Yeah, if you compute raw intensity, you can definitely see the raw intensity dropping. If our TINUS system, it's kind of harder to see the raw intensity, but I think we can still most probably see the difference in the data that it's plotted online. Then there is also a question about picking a time window, for example, like having 6-second trial tasking cognitive load in considering that there is some delay in pupil response, which time window to take. I would say, I don't know. I would most probably take all of it, or like if it's to analyze, I would leave some the first second back there. Maybe the first second could be baseline, or it depends on your paradigm. It depends if you have run some study like this before, or someone else has run such study. If you are just pioneering this, yeah, good luck. And I would say just don't take. Maybe take. I would take the whole window somehow. If it's 6 seconds, 6 seconds is not that much to omit something. Maybe the first second could be like baseline, or the first second could be not to be included. But otherwise, it's hard to know unless yeah, there is more specifics. Yeah. And there is also the question if we can use data collection from another task, for example, habituation paradigm, and or it will be unreliable. I mean, as also Velister, I think, said, like sometimes also some of the aspects of pupil of the requirements for acquiring pupil data are already satisfied in standard paradigms. For example, you may want to show the same stimuli or similar stimuli. So it depends on what you saw. If you have luminance differences, then that could be a problem. But yeah, you have to take that into account. You have to see where your subjects look, if they look at things that are same luminance or different luminance. That will affect pupil size much more than any cognitive effect.
Yeah, and the time course as well. I'm thinking about this habituation paradigm when you show like a stimulus and see whether infants dehabituate. is that the right word? Anyways, how long are you presenting that for? Is there enough time there for the pupil response to be recorded or measured? That's something to think about as well. So it's not always, yeah, sorry, go ahead.
No, I think that's actually quite an interesting question because, for example, you could look at an overall decrease in pupil size over the habituation trials. So that would be, another way of measuring habituation. And also, since habituation means showing infants the same event over and over, then you are controlling because you don't have different conditions. So that could be an advantage. I mean, it depends on where and what you're trying to measure. But habituation, I would speculate that would be one of the easier tasks to adapt. Indeed. Sorry.
Yeah, I was going to say the same. That's not always the case that you cannot look at the pupil data afterwards, and habituation when there might be tonic changes in pupil dilation. Yeah, this is a nice candidate potentially. I think
And there was this, no, this question was quite interesting about the luminance of the stimuli.
Right.
Yeah.
So I also tried an answer to that one, but go ahead, Dim. If you want, sorry.
Let's see. Yeah, in case others have not seen it, the question was, how do we test luminance of the stimuli? We made a big deal about luminance. So how do you test for luminance? Do you take the average of the whole screen? Yes.
Yeah, I think that's what we do in general, but yeah, I think it's probably better practice if you use different stimuli, different objects to control for luminance there, especially if you expect, for example, you can have objects that reveal or whatever, and infants are supposed to track these objects. Yeah, it's something that should be controlled between conditions, but yeah, as we said, it's also infants. We don't want to bore infants, so it's always a trade-off there.
So the issue is that we don't know how large is the part that the eye averages to compute the adaptation to the luminosity of the part of the screen. There are a couple of studies, not that many actually, maybe I didn't search correctly, that look into this relationship, and they can find it reliably. We could find it in our playing with the system. But you kind of need to know in advance, and if there's some reliability between subjects with this. So that's why I sort of qualified this as attempt to get to isoluminance, because I mean, technically, if you can have the same luminosity of on average in a very contrasty image and a gray, right? But you will probably not have the same patterns of dilations. But it's a first step because you don't have pupils that fluctuate wildly during the presentations. So yeah, and we are trying, as I said there, to come up with a situation that is repeatable and doable for our system, but it could be a separate algorithm that people could implement with their own trackers.
I think that's it. Any very last minute raised hands or questions? Yes, there is one last minute question. Okay, let's see. Okay, do you have any tasks that have gaze dependent measures that also record pupil information? I am new to using the eye tracker with infants, but I find that once I set the threshold to only have the pupil, it's much easier for the tracker to lose the eye when the infant moves or looks towards the corners of the screen, which interferes with gaze-dependent measures of the task. But if the threshold is higher, covers almost the whole iris, then I don't lose the eye. So do we have any tests that have gaze-dependent measures that also record pupil, like gaze contingent measures?
Yeah, we have. Yeah, we
I
haven't done
personally-
that at the same time, something like that. Yeah. But also because one study in the lab uses case contingent measures, but doesn't really control for luminance and does pupil. So yeah. But in our case, I think we don't really have seen that
Issue.
much of an issue, I think.
No.
Also, we do record gaze. We don't have contingents, but we do record gaze, and we do check gay, like which box infants look at and things like that. So, but it's indeed tricky. Like it's very often that the eye tracker, but we haven't tried not to. Yeah, we haven't tried. I don't know. Maybe it's another system, so we don't. Have knowledge.
Maybe
of
it's
that.
not the system. Maybe it's something about the layout or something. Maybe if they get into some situation where they're at the limit of like they change the distance to the screen and their eyes become a little bit blurry when they move. Or if it's a system that uses very long exposures, of course, during movements, you would want to lose, and then the algorithm has to figure out where the eyes are, and then you lose some frames. That's the same for all systems in some sense, but somehow maybe this situation is exacerbated in yours. So maybe you can play with the variables that you have in hand in playing around. Like we do this because when we were developing, we had at some point something like this, and we were just playing around in front of the camera and trying different parameters just to see which is optimal, which gets us faster to detect the eyes.
Yeah, but yeah, it makes total sense that tracking the whole iris should be easier. It's much higher contrast.
Yeah, exactly.
In this sense, yeah.
Okay, I think this is the last call for questions. None. No. Okay. Well, thank you so much for attending the webinar. It was, a lot of fun for us. And yes, look for the blog posts. It should be up on the ICUS blog in a couple of weeks, we think. And yes, again, feel free to contact us. We're more than happy to help with any pupillometry or animation related questions. Bye.
Thank you.